And again, welcome to today's webinar, From Monolith to Microservices, Containerized Microservices on AWS. Our presenter today is Asif Khan. Today with us, we also have a team of webinar moderators who will be engaging with you and answering the questions you have, Pierre, Peter, and Nathan. So make sure you submit a bunch of questions for them and test their typing skills. Asif, welcome. The floor is now yours.
Thanks, Quentin. Hello, everybody. My name is Asif Khan. I'm a solutions architect with Amazon Web Services. And in my job, I help customers design the best possible architecture to take their monoliths to microservices. In this talk of monoliths to microservices, we are going to talk about how do we go from a monolithic architecture to a containerized microservices architecture on AWS. So let's begin. So from expectations from this session, what you would learn or walk away with after this webinar would be, what is a microservices architecture? What are the benefits of it? How does Amazon ECS enable that? And what are the details of Amazon ECS under the hood? We'll talk about a recent feature, advanced feature called task placement, which helps in acceleration and speed of deployment of these microservices. And finally, we are going to use the 12-factor app as a pivot towards talking about various patterns that we have seen customers use to deliver microservices and increase agility in their organizations. So let's begin. As we all know, a microservice is a software architecture style where complex applications can be built out of small independent processes and through a well-defined contract, which is language agnostic. These services are typically small and they are very highly decoupled, and they excel at doing one thing and one thing really well. So all of us have seen this picture in some shape or form in our careers where we were coding or developing applications in a monolith. And what do we mean by a monolith? I have a web server and my whole stack, the UI, the service layers, the interaction layers are all packaged together in one package. And then I deliver this onto my deployment pipeline and then deploy this on the web server as a unit. Now this induces some amount of complexity where, for example, it's tightly coupled, it's hard to change, and it slows down development. Where microservices has taken us is it has given us these atomic units that do one thing and one thing really well. It has very clear interfaces, which are very easy to change and which facilitate rapid iteration. Microservices can be polyglot. So in the last slide, each of these services could be written in the language of choice and where the language that supports these services best. These services do one thing and one thing really well. They're independent of each other. Dependencies are managed outside of the packages, and they are decentralized. So you can then take these microservices and make them geographically distributed and expect the same experience. Finally, you build it and you run it from a conceptual perspective. Running one microservice is easy. With the advent of Docker and containers, I can open up my laptop and run these services. But running thousands of these microservices or containers is hard. And that's where the cluster management piece comes in. Amazon ECS is a fully managed Elastic service. The toolbox provides you everything out of the box that you need to leverage and deliver the best experience of microservices on the AWS platform. Amazon ECS also uses the shared state optimistic scheduling to schedule the resources needed for these microservices. And finally, Amazon ECS integrates deeply with AWS services, which we will talk about in details when we go through the 12-factor app pattern. There are two major workloads or type of microservice app workloads that we are seeing with our customers. First is the long-running apps. These are apps, for example, a video watching app or a service that stays alive. It scales up and scales down based on load, and it's easy aware and things like that. The other use case or example we have seen is the bad jobs. So if you've used a map, that map is possibly calling one of our customers who's talked about this publicly is Mapbox, and they run their data jobs on ECS, and that's the bad jobs part of it. A third use case, which is becoming even popular as we speak, is a platform as a service. For example, platforms like Convox and on other such and such things. So those are some patterns of how customers are choosing to deploy containers. So I did touch upon Mapbox. So let's talk a little bit more in detail about that. Mapbox, when you go to an Airbnb site or a CNN.com site, chances are it's powered by Mapbox. When that event happens, that event is placed in an SQS queue. Mapbox built the WatchBot library to run a highly scalable AWS service to perform data processing tasks in response to external events. You provide the messages and the logic to process them, while the Mapbox handles making sure that the processing task is run at least once for each message. Your task can be anything that works in Docker, use any language, environment variables are as inputs, and do any I/O, and finally save the outputs to S3 or DynamoDB. Mapbox has done 500 million compute hours in 2016, and we are glad to have them. A second use case is the Instacart platform as a service that we talked about. In this case, Instacart built a platform as a service coordinated through an RDS database and the same tooling for local and cloud. They are primarily a Ruby, Rails, JavaScript, Python, and R shop, and their primary domains each within their own SLA. And domains were comprised of many smallish services. Instacart used an anti-pattern of a monorepo to get there, and they built a custom PaaS on ECS. A third example is Netflix, which is pushing the envelope even further with media encoding experimentation and digital watermarking, which they are experimenting with on ECS and their homegrown solutions right now. So given those examples of ECS and how ECS is being used, let's dive deep into some of the constructs of ECS. The most basic unit of work in ECS is called a task. A task is a group of containers. The abstraction on top of a task is a service, which is a load balancer, if you make a load balancing service, and that can sit behind an application load balancer, which is a layer 7 load balancing tool. Each of these tasks or services land on an EC2 instance, which we call container instances. Each container instance has a ECS agent, which is a daemon, which talks back to the ECS service and communicates via the agent communication service. And our cluster management service and our key value store help you maintain the cluster state. All of this is powered by APIs, which can be accessed by the users. One of the features we published released right after reInvent is the placement engine, which helps you place tasks based on your needs, and event stream, which helps you capture events out of the containers and log them to CloudWatch. We have even open sourced a scheduler and the cluster state service through our open source project called Blocks, and you could extend it via the same API mechanism and use it. We have a very active Gitter channel where our engineers and our community participates around Blocks. So I welcome you to join that Gitter channel. Before we dive deep into the patterns and the different aspects of 12-factor app, let's touch briefly upon task placement. Task placement engine provides you the capability to place tasks based on placement constraints, and you can do complex math for expressions and place tasks as per your need. In this example, we're using the filter query language and use placing tasks for the my app task definition, and we're going to place 5 of them. And the constraints we're using is that these tasks should only land on T2 small or T2 medium instances, and they should not land in US East 1D. Another example is of spreading across zones and Binpacking these tasks on memory. And as you can see, the tasks are getting placed across the AZs and are getting bin-packed on the different instances that are being specified. You can also define affinity or anti-affinity for your tasks. So in this case, I have my app task definition, which will land on the group web server, and the constraints are that it should land on the group where it is a part of. And in the second example, the purple ones are the DB groups web server group, and they should not land on the web server group. It is as easy as updating a JSON file to include these placement constraints and placement strategy and build the placement. Another example is putting multiple services on a cluster in case you're heterogeneous clusters or heterogeneous services on the same cluster is the use case you are targeting. And you could send these services based on the placement strategies that you define. And finally, another example is that you could place services on distinct instances. For example, if you have a machine learning algorithm running, then you could target the G2 instances versus a web app which is in development, and you might want to target a T2 small. And as the cluster scales, the scheduling engine starts placing these tasks in the right order. And I went back. So let's talk about the 12-factor app with ECS. This is a set of reference architectures which we have seen our customers implement, which our solutions architect have helped customers get through this journey from monolith to microservices. The 12-factor app is a well-known concept, and we've talked about this for a while. What it really talks about is there are 12 aspects of coding and building a software that helps you get to the agility that you need. Personally, I feel I could group them in a mental model of code, ship and release, admin processes, tools, which is another way of saying it, and monitoring, or disposability, concurrency, and port binding. So let's see how each of the patterns addresses the different concerns of the 12-factor app. The first example is of our example microservice. I have written code and I've changed a UI or a service into a microservice, or I've taken an existing code and written a Docker file to containerize. I can easily deploy this on the ECS cluster, auto-scale it, but I can also load balance this behind an application load balancer. As I said earlier, application load balancer is our layer 7 load balancer, which provides you features like path-based routing and WebSockets and things like that. Now, the application load balancer can be put behind an Amazon Route 53 DNS service where you can look up or redirect traffic through the logical names. You could also use Amazon API Gateway for things like throttling, API usage, API keys, and make your API scale the way you want. On the other end of the spectrum, these containers or the code could talk to Amazon RDS, which is a managed database service, to interact with and store user data or application data. The images that are being deployed on the containers are stored in Amazon ECR, which is the container repository, a private container repository, following all the IAM policies and rules that you have defined. The IAM policies and rules you define apply to the task level and also to ECR, and we'll talk about this in the next slide in details. Amazon CloudWatch provides us the monitoring and the logging capability that we are needed to make sure that our environment is up and give us the operational excellence part of it. This does address the code base, the tooling, and the monitoring aspects of the 12-factor app as we go. Another pattern we have seen with customers implement is the automatic service scaling. When ECS scales the services, for example, in this case, task A is behind a load balancer in zone A and task B is behind B. These ECS will publish metrics such as CPU or memory. And from Amazon CloudWatch, you can trigger the scaling policies, and Amazon ECS will pick up those scaling policies and scale the tasks based on your need. As I said earlier, IAM roles or security is job zero for us. It's a top priority for us, and that's where we have built task-based roles, so you can rely on your task being able to access only the resources they are allowed to access. In this example, task A has the appropriate role to access Amazon DynamoDB, which is a scalable managed NoSQL database, but task B does not have access to Amazon DynamoDB. And this you can do from the IAM roles, that like the standard way we create IAM roles and attach them to a task. And also in this example, task B has access to Amazon S3, but not task A. Continuous deployment is a big factor of how we roll out software and how the 12-factor app comes alive. So I'm a developer, and the nirvana for me is I push code and everything should be deployed, everything should work. In reality, it's a little less of that. So I push it to a code repository, which in this case is AWS code commit. It could be GitHub or any other repository of your choice. Now, once I put my code commit, I could probably have a code scan tool that scans the tool, which is not on this picture, and trigger that pipeline. Once that code push has happened, AWS Code Pipeline, which is a development or a pipeline workflow tool, routes it to Amazon Code Build, AWS Code Build. Code Build is a managed build server. More in the days like old days, we could think of running our own Jenkins server, but now AWS Code Build provides you the managed capability where you can submit a job, and the job Code Build runs the build, and as long as the Docker file is correct and you've specified the correct build artifacts in build steps in build spec YAML, it goes through fine. One of the most amazing or interesting things for me on Code Build is the pre-hooks and the post-hooks. So anybody who's been through Jenkins understands and has sympathy towards the plugin management piece of it. With pre-hooks and post-hooks, I can call other AWS APIs like AWS tag, the Docker image, push the Docker image to the Amazon ECR repository, and go from there. Now, once the build is complete, it gets pushed to Amazon ECR, which is a private repository. Now with Amazon ECR also, we have IAM roles, we have fine-grained controls, and we have also namespaces that could be leveraged for security. Once the image is available, Amazon ECS would pick that image and deploy that image to the cluster. Now, the cluster can be comprised of multiple instance type or a single instance type, which auto-scales the infrastructure at the infrastructure level also. To keep in mind is spot instances. Spot instances are a great vehicle to save cost and make a cost-optimized architecture. Spot gives you typically 80% discount over on-demand prices, and Spot Fleet helps you make sure or manage the availability and your service uptime. And we've seen with great success customers using Spot instances across multiple use cases. Another key factor of cost optimization or agility is reserved instances. If you have not looked at reserved instances, you should look at reserved instances in a way as a way to allocate capacity and save cost. This is all great. Now I pushed code as a developer, I made my container, I'm able to deploy to a cluster which other applications can consume or can service the user. But what happens when I make a change to code? So I made a change, it's a security bug or it's a critical bug, and I made a change to code and I pushed that code. From the same infrastructure and from the same workflow, you could take the code pipeline and update stack. AWS CloudFormation delivered two great features last year. One was the cross-stack variable passing, and the second was the update stack. Now, when you look at this infrastructure that is being built by the pipeline, you could have a stack for provisioning ECS resources, a stack for provisioning CI/CD resources, a stack for provisioning the network resources, and once you trigger that, those are different stacks. Now, when a new service becomes available or a new image is getting pushed, all we need to do is update the particular stack, which is in this case ECS, and not redo the complete set of stacks. When I do the update the stack, it picks up the changes that happened on the stack. For example, in this case, an image changed, and it tells Amazon ECS to update the service with the new image. And in this way, through a rolling update mechanism, all the copies of that task or service gets the new image out of the box. And the continuous deployment pattern that we see here addresses almost all of the 12-factor app concerns. One thing to call out here is you could even build in an image scanning tool with AWS Code Build or through the code pipeline that you can actually build the image and send it to the scanning software like Twistlock and take this. Once the results is up, then you push it and store it in Amazon ECR or integrate that with Amazon ECR directly if you need to. We talked about rolling updates and how the AWS platform and different pieces give us the agility to roll out. Some of our customers have seen great success in blue-green deployments. At a high level, the blue-green deployment is a way to manage rollout of new features with a higher degree of confidence. So in this example, what you find around 53, and the green service is which is servicing my traffic, but the blue is the new version of the service that I am deploying. Now, I could throttle up slowly the traffic to my blue task and redirect some traffic to that and see how that performs. And eventually, when I have enough confidence on my blue task, I would change that to the green task and shut down the old green task. That's how we have seen customers do blue-green deployments. One of the most important aspects of containerization or 12-factor app in microservices is secrets management or config management. AWS has released EC2 Systems Manager Parameter Store, which is a parameter key value store which is encrypted by KMS keys and backed up by the HSM modules that AWS supports behind KMS. Now, you can access that key parameter store via the IAM roles that you can attach to the task. So in this example, task A might have a database password or some key it is trying to access, which is a secret, and he tries to access the parameter store. It was not assigned the correct role, so it does not get access to the role, to the secret. But task B, on the other hand, has been assigned the correct role, and you could group these secrets or in the parameter store value by container names, and task B get access to the secrets, and this helps you achieve the code base which is independent of each other and the dependencies live somewhere else. This also helps you achieve dev fraud parity and logs and admin processes that go on from there. When we talk about containers and microservices at scale, referencing them with logical names is of high importance instead of their physical names, because the physical names could change due to the lifecycle events of the container or of the infrastructure. But having a logical name-based routing capability is paramount. So in this reference architecture, what you see is we have a root within mydomain.com. mydomain.com goes to the application load balancer and routes me to the portal target group, and I do not care about what are the physical names or the port numbers out there. And you can always do dynamic port mapping with application load balancer. Now, when you look at mydomain.com/weather, which is a path-based routing, that takes me to a different weather target group, and I can service out of that. Now, whether this container shuts down, brings up, or things like that, I can still access it via the target group. So this is one of the patterns or ways our customers have been implementing service discovery with Route 53 and application load balancers. Another pattern which is becoming increasingly popular with our customers that we have seen is using event stream that we released to do service discovery. So when a container has an event, a lifecycle event, for example, a container got created, that is published as an event stream. And if you can see the JSON there, it basically is an event rule that says that when the state change happens on the task, this is what you need to emit. And the last status was running. And that got emitted. We catch that through Lambda, and through few lines of Lambda code, we can actually do an upsert operation on the resource record set on Route 53. On Route 53, what we have is a logical way of referencing the physical container, which is DB2 10.1.018 in this case. And similarly, as containers keep coming up, I can keep an updated copy of my service discovery service registry that can be used for service discovery. And even if a container comes down, then I could remove these from the service registry to make sure other containers can find each other and keep my service highly available and fault tolerant and scalable. An important aspect of enterprise IT and doing microservices in enterprise IT is governance. We have all been through the scenario where stacks come up and there is less and less control. Enterprise IT wants to implement best practices and control standard governance and also enable the agility and the self-service time to market that the developers desire. AWS Service Catalog brings the two worlds together and helps developers develop faster and organization control standardized governance through various mechanisms. How does AWS Service Catalog help us build this governance in the portfolio? So in this case, an administrator creates a portfolio and he lists the product X, Y, and Z stacks in that. He authors the template, he creates the product, and he adds in constraints and grants access to various product teams or developers or users who use them. The developers or the teams or the users browse these products from the portfolio, and they could only launch this product if they have the correct access and the grants that they need. And finally, once they deploy the stack. When the stacks are deployed, this gives us notification back to the administrator and the user. So it gives us the developers and the teams that are deploying these stacks a finer grain control or a way of launching these stacks following the best practices and the compliance standards that are needed by their enterprise IT. This also helps them ship and back services and release and run processes in a controlled environment and really fast. It also gives dev and prod parity between the different systems so that you don't have to you're not launching different stacks or different flavors of stacks that every developer might change. It also helps you processes in admin processes that you can innovate and build admin processes and logs. Once the underlying heavy lifting that you see has been done using these different reference architectures and different tools that an AWS platform provides you, the DevOps team can start focusing on delivering more value in terms of driving, for example, exception-based development workflows as an example, and the developers can start writing the best code or writing the best code that is possibly solves the problem in a much more elegant manner. So the separation of concerns and addition of value, like making people add value to the process, is what really microservices provide you. And AWS provides you the platform and the toolbox to take the different microservices patterns and apply them using the different toolboxes. I would highly encourage you to build a sample microservices. We have a GitHub repository called github.com/AWS Labs. And if you go and search for ECS, you'll find quite a few projects, and we'll love you to have a go at it, try it, and see how you feel about it, learn about it. We have documentation to help you out there. We even have blogs, a series of blogs that are out there, ranging from deploying programming languages to deep learning algorithms to how to do overlay networking and things like that on ECS. And finally, try out a sample POC in your environments, in your test environment, dev environment, production environment, and deploy these and tell us about your experience. So with that, I would say thank you.